Hello, everyone. Welcome to my talk. Thank you all for being here. So, this is the title slide of my talk. I always put astronomical pictures on my title slides. This one is a bunch of galaxies which are distorted by the gravitational lensing effect so that they look like an evil smiley face, which I thought was appropriate for the title of the talk, which is Type Punning in Modern C++. Except actually, that title is also not actually the title of the talk. So let's talk about the title of the talk. If I would have named the talk Type Punning in C++, then it could sound like you could actually do type punning in C++. Turns out that you can't really do type punning in C++. So maybe a better title for this talk is How Not to Do Type Punning in C++. But that's also kind of a boring title because then I just say, okay, you can't do type punning, that's it, we all go home, right? That's boring. So I think a more appropriate title for this talk would be How to Write Portable Code that achieves the same effect as type punning in modern C++ without causing undefined behavior. And that is exactly what we're going to talk about today. So type punning, what does that mean? Punning, pun, is an English verb, right? So it means a joke exploiting different meanings of words, essentially using a word with a meaning that you didn't expect or that isn't appropriate for the context to create a humorous effect, okay? So then in programming, if you talk about punning, type punning means subverting the type system by using an object of one type as if it were an object of another type. So let's be a bit more concrete. Let's say we have an object of a type cat, okay? Let's say we have a cat here. And then basically type punning means you're going to tell the compiler, okay, so we have a cat here, but you know what? Actually, it's not a cat. It's a dog. Okay? That's what type punning is. And then the compiler will say, okay, well, it's a dog, right? So if it's a dog, it means I can take it on the lead and walk it, right? And it's going to try to do that. Have you ever tried to walk a cat? Do you know what happens? So the results are different, right? So I used to have a cat. Usually, when I try to do that with my cat, the result was something like this. This is one possible result. Another possible result, you might end up with something like that. This is also possible. Or, if you're the right kind of person with the right kind of cat at the right time and the right place, maybe it will just work. That's also possible, but you never really know because it's a cat, it's not a dog. So you're not supposed to do that. So let's look at some code. So this is an example from Luna. She's on Twitter, Luna Sorcery, and she has tweets about very interesting C++ stuff, so I recommend check out her Twitter account. So this is from there. So here we have a struct widget and a struct gizmo. And they have two functions which are completely unrelated, right? So they're not inheriting from each other or anything like that. So they're just two completely different functions. And what we do is we create a gizmo, and then we cast it to a widget, and we call widget do something on that object. Okay? First question, is this code going to compile? Yes? Okay. So, of course, the interesting line is this here, right? So we have a gizmo, we cast it to widget, which is a completely different type. Yes, it's going to compile. Why? Well, it's a C-style cast, right? So let's look at the standard, what the standard says about C-style casts. It says, okay, if you have a C-style cast, then the compiler's going to try a const cast. If that doesn't work, it's going to try a static cast. If that doesn't work, it's going to try a bunch of other things. And if everything fails, at the end, it will try a reinterpret cast. And then if that succeeds, it's going to do that. So what you effectively have there is a reinterpret cast, right? Which you didn't write, but that's what the compiler did. So one kind of corollary from that is please don't use C-style casts because you don't really know what they're going to do. But OK, so this is effectively a reinterpret cast. So this is going to compile. Next question. What is it going to do? UB, yeah. But what is it actually going, like if you actually compile this and run this, what's going to happen? It prints gizmo, other ideas? It prints widget, okay, let's look at it. Let's check out Clang with optimizations on, because that's obviously the interesting case. So yeah, it prints Gizmo, okay? So, it's like the first virtual function, so it's just gonna call that. And okay, let's try the same thing on GCC, different compiler. Whoops, the compiler just optimized away your whole program. So what the compiler is doing here is it's saying, okay, well, you're casting a Gizmo to widget. That is only allowed if it's actually a widget, if it's actually originally an object of type widget, which it is not here, which means that this can never happen. You can never reach this line of code. This is impossible. So I'm going to optimize away all the code paths that lead to this line of code because you can never call it, right? And that's what UB is. So and then in this case, it's just the whole program. So this is kind of what UB is. It's not an error. It's this cannot happen, so the compiler is going to assume it's not going to happen and optimize based on that assumption. This is one of the things that UB gives you. And then all bets are off and anything can happen. So we already saw that two different compilers do completely different things. There's a great talk by Barbara and Ansel from last year's CPPCon about basically an hour with examples like that, like what undefined behavior does, what it means, like what surprising effects it can have. So I definitely recommend you check that out, but we're gonna not talk about that so much. We're gonna talk about very specific type of thing which we're doing, which is this type panning, where you have an object of one type and you convert it to an object of another type. It's UB in this case. How do you make it not UB? How do you make it work? So I looked at this and kind of found that there's broadly 3 different categories of this kind of type panning thing. So one is you have 2 unrelated types, for example, float and int, or widget and gizmo. And you want to type pan one to the other. Then there's another case, which is this, where if you have an object and you want to look at the bytes of that object, or in the other way, you have bytes and no object, and you want to look at those bytes as if they were an object. So you're casting between a bunch of bytes and an object of some type. And then there's this third category, which is a bit weird, where you have an object of one type, which is composed of other types, and you want to cast it to something else that is composed of these types, like an array, for example. So this is a bit weird. We're going to look at this at the end. Mainly, we're going to talk about the first and the second. So let's start with the first, right? We're casting an object of one type to an object of another completely unrelated type. Why would you ever do that? Turns out it's actually really, really useful. So let's look at some code where this is actually happening. So this is a famous piece of code from the 90s. Sure, some of you have maybe seen it. It's from Quake 3, which is a very successful first-person shooter from the 90s, where you want to compute the inverse square root, which is something that in a video game you need to do, or in any kind of 3D thing, you need to do all the time, because you need that to normalize a vector, which means you need that if you want to know a direction or an angle, compute a reflection. You need to make this computation all the time, so it needs to be really, really fast. This is how they implemented this in that code, which was C code in the 90s. So obviously, just comparing 1 over std sqrt is kind of slow. So they found a very clever way of doing this. And this is the original code, except the comment contained kind of a slightly inappropriate word, which I redacted. But otherwise, this is the original code with the original comment. And what's happening here is, of course, these are the 2 interesting places here. So you get a float, and you want to compute the inverse square root of that float. So you look at the bytes of that float as if it were an int, okay? And then you do this weird bit shift operation with this magic number, which transforms it into another int, which then you cast back to a float. And the trick is that float, that new float, is kind of more or less close to, due to the particular bit patterns that are at work here, it's relatively close to the result you want, 1 over square root. So what you then do is you do 1 iteration of Newton-Raphson on that, and then you bring it even closer to the result. And after that line, it's going to be within 0.1% of the result you want, which is good enough for this particular game. And that's really fast. It's just a few instructions. Of course, so this gives you what you want. It works. But of course, it's UB. And it's UB even in C. This is C code. Even in C, this is UB, okay? So why is this UB? Well, you have a float and you pretend it as if it were an int. And then you do it all the way the other way around as well. So these two lines of code, they violate this particular rule from the standard. So let's look at some standardese. The standard says, well, if a program attempts to access a value of an object of one type through an object or reference of another type, then that's UB unless it's either the same type, or it's like the signed or unsigned equivalent of that type, or it's char or byte. If it's anything else, this is UB, which means if you have an int and if you have a float and then you look at it as if it were an int, that's UB. You can't do that. So what can you do? So I actually, so my background is I do audio and music technology. So I worked at a company and they had this kind of code where, so in a video game, you would want to do this inverse square root. What you do in music a lot is compute the exponential, because in music you have like linear scales and logarithmic scales. You have to convert between them very frequently. So they had similar code where it's like a very fast exponential function, which also was using this kind of bit twiddling stuff. And then I left that job. I went to another music technology company, and they said, okay, we're not going to use reinterpret cast. We're going to use unions instead. So they knew that reinterpret cast was UB. So they were using something like this. So I would write this Quake code in this way, where instead of doing the reinterpret cast, you would have a union and then of a float and an int, and you would write into the float and then read the int, and then write into the int and then read the float. Is this better? Nope, same thing. So what you're doing here is, so you wrote a float into the union, and then you're reading it as if it were an int. So you're doing exactly the same thing, right? The standard says, in a union, only one member is active, right? So if you write into the float, then the float is the active member. The int doesn't exist. You can't read that. If you're doing that, you're back here, right? You're trying to access the float as if it were an int. This is not the same type. You can't do this. And it turns out, okay, first of all, don't use unions, okay? Use std variant. The std variant is the version that is safe, which doesn't let you do that. Unions are pretty much useful for implementing variant. Don't use them for anything else. But kind of the main insight here is that it doesn't matter what technique you use, whether it's reinterpret cast or like this union trick or whatever. It's not the technique, it's what you're trying to do, like looking at one object as if it were an object of a different type. And that's just not a thing in C++, right? This is just UB regardless of which of the techniques you use. So this union trick is also UB, except on GCC, which explicitly allows it. But if you want to do cross-platform stuff, then you can't do that. So then it turns out, well, you can't do type punning in C++. Okay? So this is basically the where we are right now. But then you might say, well, but it works. You know, if you write this code, you compile it. On GCC, it says in the documentation you can use the union trick, not the reinterpret cast trick. On other compilers, maybe they don't say whether it's okay or not, but then you look at the assembly you get, and you get the right result, and then you're like, yeah, but it works on my machine. So you put this in production, and I have this discussion over and over again with developers who say, well, but it works. So why you know, standard committee people, you talk to me about the standard. No, like this works. I know this. I'm an engineer. Unfortunately, yes. I mean, if you're writing for a specific compiler for this specific machine, and you know compiler, the compiler says it's fine. It's fine. But if you want your code to work on different platforms, you're not programming against the compiler. You're programming against the C++ abstract machine. Okay, and the C++ abstract machine has rules. And if you do this kind of stuff, then basically what you're doing is, so I live in England. In England, we drive on the left, yeah? So what you're doing, if you're doing this kind of stuff, is you're saying, you know what, but I can drive on the right. You know, the rule says, you know, I have to drive on the left. But, you know, if you look at the right lane, there's no cars there, right? So, you know, I can get into my car, drive it on the right side of the road, and get from A to B, and I'll be fine. And you know what? Maybe on this particular road, at this particular time of the day, you will be fine. if you want to do this anywhere else in England on any other day at any other place, this is probably not such a good idea. Okay, so this is what this is. And then at some point I found out about these rules. We had all these discussions. This is all UB. You can't do this. And then I was still left with this thought. But why? Right? And for a long time, myself, I didn't understand this. I was like, yeah, but these are just bytes, right? This is a computer. It's a compiler. It's generating machine code. So whether it's an int or it's a float, there's just bytes. Like, why can't the compiler just look at those bytes and interpret them as an int or as a float or whatever, right? What's the problem? Why is it not allowed? Turns out there's actually at least 4 reasons why this is not allowed. And this is where it gets really, really interesting. So we have aliasing rules in the language. We have object lifetime rules. We have alignment rules. And we have rules whether or not a particular value representation is valid. And if you do this kind of type punning stuff, you might violate at least the first 2 and possibly the other 2 as well. So what we're going to do for the rest of the talk is we're going to look at these things and try to understand how they work and what you can and cannot do. Let's start with aliasing rules. Okay, so aliasing rules. Let's look again at this rule that if a program tries to access an object through a reference of a different type, it has to be either the same type or it has to be char or byte. And then there's this footnote which says the intent is to specify those circumstances in which an object may or may not be aliased. What does that mean, aliased? So let's look at this. So here we have a function. Takes 2 pointers, 2 integers. It sets the first one to 1, it sets the second one to 2, and then it adds the second to the first. Okay? Very, very easy, right? Let's call this function. Okay, so we have 2 integers, and then we are passing pointers to these integers to this function, and we return x. What is this program going to return? 3. Okay, you're very good. Okay, cool. This is very easy stuff. Let's add a little bit of an evil twist. Let's say we only have 1 integer, and we're going to pass 2 pointers to the same integer into that other function. Question number 1, is this valid C++? Yes. Question number 2, what is this program going to return? 4. Okay, brilliant. You're really good. So what's happening here is that B is aliasing A, right? Which means we have 2 pointers that alias each other, which means they point to the same object. But because they're the same type, they're both pointers to an int. That's okay. You can do this. This program runs. This program returns 4. So the rules in C++ are that this aliasing stuff is fine if they're the same type. So let's look at some assembly. Let's look at some compiler explorer stuff. So it's again this function here. So what does it compile down to? So we set the first one to 1, we set the second one to 2, and then we add the second one to the first. So if you look at the right-hand side, the instructions are literally that, okay? You store 1, you store 2, and then you add 1 to the other. Okay, this is the assembly you get. Not very surprising, right? Interestingly, not every language has the same aliasing rules as C++. So my first programming language actually was Fortran. My background is in astrophysics originally, many years ago. So in astrophysics, we were programming in Fortran. And Fortran has different aliasing rules. So in Fortran, 2 references can never alias each other. So the compiler can always assume that if you have 2 references, different references, that they will reference 2 different objects. And so it's just a different aliasing rules. And the astrophysicists, they really like to say Fortran is faster. You C++ people, you're good, but like Fortran is faster. Fortran code is faster. Fortran compilers generate better code. And you know what? They're right. So let's see if I remember how to write Fortran. Let's write the same function in Fortran. This is how it looks. Yeah, not surprising, just different syntax. But interestingly, on the right-hand side, we now have more optimized code. We only have 2 instructions here, right? So this is actually going to be faster code. So what the compiler can do here is it can say, well, okay, so we're adding 1 to the first, integer, 2 to the second, and then we're adding the second to the first. But we know that A and B are different objects, which means we know that if we modify B, that A has not changed, okay? The Fortran compiler knows that after B equals 2 has run, A is still 1. Okay, and what it then can do is it can reorder the A and B assignments and squash the other two, because it knows that A hasn't changed. And this way it can generate more optimized code, because the aliasing rules are different. Okay? So in C++, again, we have the rule that pointers, if they're of the same type, they can alias each other. But if we had the rule that every 2 pointers could always alias each other, then the compiler would always have to assume that if you change anything, anything else could have changed, right? So it could never do these reordering optimizations, and all our code would be really, really slow, and that would be not a good place to be. So C++ needs to have some reasonable rules when to assume that something can or cannot alias each other. And in C++, the rule is that if 2 pointers are of different unrelated types, then they cannot alias each other. So if we slightly modify this function and we have a pointer to an int and another pointer to a float, then the compiler can assume that those pointers point to different objects. So then it can assume that after you say B equals 2, A has not changed. And it's going to optimize based on that assumption, right? And if you then try to circumvent that by saying, okay, we're going to try to pass 2 pointers that point to the same thing by reinterpret casting the float to an int, the compiler has already compiled the function, assuming that this will never happen. So if you do this, this is UB, which means your code is probably going to do something, but probably not what you expected. And the value you get doesn't mean anything, okay? So this is strict aliasing. This is one of the reasons why you can't do this kind of stuff. There's an article by Shafiq. You can Google it, you can find it, which goes in a lot more detail about these aliasing rules. So if you're interested, I recommend you read that. Right, so this is aliasing. Let's look at the next one, object lifetime. Now this is more interesting. So so the aliasing rules, they exist in C as well. This is like C and C++ stuff. Now we go to like C++ land. And C++ is one thing that C doesn't have, which is classes, but what can they do? Constructors, exactly. So C++ has constructors and destructors, which means objects get created and destroyed, right? So object in C++, if you think about Schrödinger's cat, which is like simultaneously dead and alive, that's not a thing in C++. In C++, objects are either dead or alive, right? And it's very, very simple. And let's look at this with this kind of example where we have bytes and we want to cast them to an object. This is like the second case. So this is code that actually is okay in C, where you have some memory that you've allocated, okay? And you have a struct, like a type. And then you say, okay, we're going to allocate some memory, and then we're going to cast it to an object of type X, right? Is this okay? Now someone's nodding. Okay, so in C, it's okay. In C++, this is UB. This is undefined behavior. This is not allowed in C++. Why is that? Because objects have lifetimes, right? So the standard says objects have lifetimes, and the lifetime of an object essentially starts when the constructor runs and ends after the destructor has finished, right? So you construct an object, you run the constructor, then you have an object, and in that time period, the object is alive, and then you destroy it, and then it's dead, or it doesn't exist, okay? And then it says if you have a pointer to an object, then before the lifetime of an object has started, or after the lifetime has ended, you can't really do very much with that. You can have a pointer, but you can't really use it. And the same is true for references. So before the lifetime of an object has started, or after it has ended, you can have a reference to an object, but you can't access the object using that pointer or reference, and you can't call a member function of that object. You can't really do anything with it. And if you do that, it's UB. Okay? And this is exactly what we have here. So we have some memory, we access it through a pointer to an object of type X, but there is no object of type X. Okay? We have not created one. And then someone said, oh yeah, but we have this new thing now in C++ called std launder. Now I mixed it up as well. So std launder, maybe we can launder the pointer and then it's going to be fine. Turns out, no, launder has nothing to do with this stuff. Forget about std launder, it does not help here. Std launder is used to obtain a pointer to an object that exists, okay? Std launder never creates an object. So std launder does not help you here. It cannot create objects. The standard actually says exactly what can create objects. It's this part here. It says an object is created by a definition, by a new expression, when implicitly changing the active member of a union, or when a temporary object is created. These are the only 4 things that can create objects. And here, you're not doing any of these 4 things, okay? Which means you have not created an object of type X. It's not there. It has not been brought to life. And if you then access this blob of memory through a pointer to an object that doesn't exist, you get UB, okay? Now you might say, okay, this is a kind of contrived example. Why would you allocate memory and then access it in this way? But there's a slightly different case which occurs a lot more frequently, where you have a bunch of bytes that come in, for example, from the network or from a binary file, like that you maybe have serialized at some point in the past, and now you want to deserialize it. You have like some kind of stream or like data or binary stuff going on, and you say, okay, so I know that these bytes are an object of type widget because maybe I have serialized an object like that last time, you know? So I just want to take those bytes and like access it as if it were a widget because I know that the bytes represent the widget. And so you do this kind of thing where you kind of take these bytes and then cast them to this widget, but it's UB because you have not created an object of type widget, okay? You have not started the lifetime. So you can't do this stuff, okay? This is UB. Of course, this is a common use case, right? Deserializing something from a file or from a network stream, a lot of us need to do this kind of stuff. So how do you do this? Okay, how do we fix this? So, depends. I mean, if you go back to this situation where we have some bytes and we want to access it as if it were an X, right? We need to create an object of type X. So it means what we can do is we can placement new an X into it. And this actually, placement new will actually run the constructor. So then you actually start the lifetime, right? You actually create an object of type X. So what's happening here is that you have an array, but then if you placement new an object into that array, then it's not an array anymore. Now it's an X. So we say the array provides storage for the object. And char arrays and byte arrays have this magic capability that they can do that. They can provide storage for another object. So now you've created another object, and you placed it into this array. So now the array is gone, and you actually have an X. So it would be fine, except, is this okay? No, why not? Alignment, yes, so that's yet another problem. So this is, in general, UB because of alignment, okay? So what does that mean? So, you know, again, when I was starting to get into C++, and I was learning all these things, how all this works, I had this like mental model in my head of how a computer works, okay? And so how does memory work? Where do objects live? And I always imagined it as this kind of tape, you know, like a Turing machine, which has like a tape. And there's all these memory addresses, and then you have an object which just lives somewhere in that memory. Unfortunately, that's not how it works. So if you look again at the standard, it says that object types have alignment requirements which place restrictions on the addresses at which an object might be allocated, okay? So not every object can live at any address. So it's not like a tape and then you can just pick any address and put an object there. If you look, for example, at a 64-bit system, so like the word size is 8 bytes, so I just kind of arranged the memory like in chunks of 8. And then depending on the alignment requirement of a type, it can only live at certain addresses. And typically, for fundamental types, the alignment requirement is the same as the size, which means that if you have an object that is 8 bytes, like size t on a 64-bit system, so an object of size t type can live here, it can live here, it cannot live in between. It has to be aligned to 8 bytes, okay? Same with a 4-byte object like a float. A float can live here, it can live here, it cannot live anywhere in between, okay? This is what alignment requirement means. Now, if you look at an array of 4 chars or 4 bytes, they have the same size, but a single char is only 1 byte. So chars don't have an alignment requirement. They can live anywhere. So arrays of chars can also live anywhere. So an array of 4 chars can live at an address like this. That's totally fine for chars. It's not fine for a float. So if you create an array of char like this, and then you try to placement your float into that, you get UB. So you can't do that. There is a workaround, obviously. If you do it on the stack, you have aligned storage, which is pretty much the same, except it aligns things correctly. If you are on a heap, you have other guarantees. If you get something back from new, then there are guarantees that new is always going to return a pointer that's aligned to for at least any object of fundamental alignment. So that's going to be fine, unless you have an object where you specified it has to be over-aligned with align as and stuff like that. So yeah, you have to be really careful with the stuff. You have to make sure that if you put an object somewhere that that memory is aligned properly for that object. But this is kind of a special case, right? That's not typically what you want to do, like put objects somewhere. You just want to look at the bytes and do something with them. So let's go back to this case here, to the Quake code, where okay, we have a float and we want to look at it as if it were an int. So how do we actually fix this, right? So we figured out this is UB for a whole bunch of reasons. How do we do this? Sorry, say again? Copy the bytes, exactly. This is exactly what you do in C++ 17 at least, and before. This is the cure, memcpy. This is what you can actually do. So if you are back here, this is UB, you just replace these things by memcpy. So you memcpy the float into the int, and then you memcpy the int back into the float. And then typically everyone says, yeah, but this is not what we want. Like, memcpy is expensive, it's gonna copy things. It's gonna be more instructions, it's gonna, like, this is not what we want, we just want to look at the bytes. Turns out, well, compilers are really good at this, Trust your compiler. If you write this, your compiler knows what you want to do. You're like, oh, so you have an int and a float, you're memcopying the float to the int because you want to access the bytes. So I'm just going to access the bytes. So let's try this. So this is the code, which is UB, compiled on Clang. Let's replace the casts with memcopies. And let's look at the right-hand side if the generated code actually changes. Nope. You get exactly the same code, okay? Except that this is not UB, this is portable, right? This is the difference. Okay, let's look at GCC. Same thing, the code that is UB. On GCC, it happens to compile to what you want. Okay, let's replace this with memcpy. Same thing, okay? Exactly the same binary machine code. Now, someone said to me, yeah, but surely the Microsoft compiler is not that clever. Okay, let's try this. Microsoft compiler, same code, same thing, okay? So all modern compilers know what that means, and all modern compilers will do the right thing. There's a question? Sorry, can you wait for the mic, please?
No? Oh, thanks. Could you please go on the previous slides, original implementation of QSQRT? Yeah, here. So here you not just observe y as a sequence of as int, you actually dereference it immediately, right? So effectively you do copy in this case too, right?
Well, notionally, this is not a copy. This is just you're casting the pointer to a pointer of a different type.
Yes, but then you dereference it and you copy it, assign it, right?
You dereference it.
Yeah, that's
you assign and you write a new value into it. Yeah.
right, right. So here you do not just observe, you copy it as if it were an int or as if it were a float.
So you modify the bytes using operations on integers, yes. I mean, you're not creating a new object, but you're modifying its value.
No, you do. You have float number and you have a separate integer I, right? You have you have a distinct memory. So in both cases, you do have distinct memory. It's if I were a reference, like in reference, you were initializing it with the dereferenced y casted to int star, then you wouldn't have new memory. But here you explicitly allocate new memory for int.
Okay, let's, I think there's more going on here. Maybe we should, I think this is a longer discussion. Can we talk about this after the talk?
Yeah, sure.
I'm not exactly sure what you're trying to get at, but let's talk about it after the slides are finished, okay? Right, so we found out that we can do this memcpy trick, and it's going to do the same as if you do the cast, okay? Let's try to generalize this, okay? Because in C++, we always want to, if we discover something useful, we want to put it into like a little library or a little function and reuse it. So let's see how we could reuse this. So let's say we have an object of type T, and we have an unrelated object of type U, and we want to type pun a T into the U, okay? So then you would memcpy the T into the U. Would this always work? No. Okay, so there's a few things you need to take care of. So first of all, they have to have the same size, obviously. Okay, otherwise this is just not going to work. So we can assert that they have the same size. There's another condition here. When can you copy things by memcpy? Like, it needs to be very good. You people are great. Trivially copyable. Okay, so both of these types need to be trivially copyable. And then it works. Okay, then we can do this. So what we can then do is we can just take all the stuff and package it up in a nice, convenient function. Let's call it bitcast. So that's exactly the same thing, except I put the 3 static conditions into like an enable if, and then I wrapped it in a little function. So what we can now do is we can, in C++ 11, 14, 17, we can write this and then use that instead of the reinterpret cast thing. And it's going to just be like a drop-in replacement. Just replace reinterpret cast by bitcast. And instead of casting the pointers, you're casting the values. And then you're fine. You get the same output, but it's safe. Okay, it's not UB. In C++ 20, it gets better because we standardized it. So now it's still bitcast. So you can just use it. You don't have to write it yourself. And it gets even better than that. So this is how you would write it in C++ 20. You just replace the reinterpret cast by bitcast, and you use values. But because it's C++ 20, of course, it's const expr. So you can do it at compile time as well. Okay? So this is basically the solution we have in C++ 20 for this problem. And bitcast, basically, for this kind of stuff, is a drop-in replacement for reinterpret cast. It's safe. Use it. It's awesome. There's one last little thing. So if you look at the definition of bitcast in the C++ standard, it says, so it's doing like the thing that we just discussed. Except there is this sentence. If there is no value of type 2 corresponding to the value produced, the behavior is undefined. So you still have a case where you can get UB. What does that mean? Well, that's the last thing on our list. It's like when a value is actually valid. When does a value represent a valid object of type T? Okay? And basically the rule is if you do this kind of stuff and you have a Y which has a certain bit pattern, or like byte representation, and then that representation does not correspond to a valid value of the other type, which is instead in this case is int, then you get UB again. So now we have to think about when values are actually valid, not valid. Can we get like bit patterns where this would be UB? Maybe. So you have to like think about it for every time you use this. So here we are punning a float to an int. Okay, so let's say we have a float. how do float look like? Like what byte representation do they have? And on all modern machines that I know of, floats are IEEE 754, okay? So then there is a static method somewhere, is IEC 599 or something like that, I always forget the number, which lets you check at compile time whether your floats are IEEE, which they will be on every machine that we nowadays use. And if they are, then you know, okay, in IEEE, every bit pattern corresponds to a valid float, okay? Some of them will be nonce, some of them will be signaling nonce, so you might get a floating point exception, but at least it's defined behavior, it's not UB. So any type of bit pattern that you can have there corresponds to some kind of value of float. What about ints? So it depends on how you represent ints, but in C++20 we adopted this paper which says signed integers are 2's complement. So now it's actually defined how the bit pattern, what the bit pattern for signed integers means. And 2's complement basically means, again, that every possible combination of bits will be a valid signed integer in this case, okay? So that means that for this case, if we have a system with IEEE floats, if you do bit casting between floats and ints, you're fine. It will never be UB if you use std bitcast, okay? So this is really cool. So now we can actually do this stuff. Unfortunately, you have to kind of repeat this analysis every time. If you have like other types, you have to ask yourself this question. If I have an object of type T and it has these bits, and you pun it, you bitcast it to an object of type U, can I have an object of type U that has these bits? And there are cases where this is not the case, right? So we saw, for example, alignment says that pointers can only have certain values. So for example, if you have an integer, which is 7, and then you bitcast it to a pointer to a size T, then 7 is not a valid value of a pointer of size T, because a pointer of size T has to be aligned. It cannot have that value. So if you were to do this particular bitcast, you would get UB. So you need to think about the types and what values they can have. But if you do that, then you're fine. And now we have this bitcast thing, which is a standard, reliable, safe method to do this kind of type punning stuff. So this is where we are in C++20. I think this is a really powerful tool. There are still some cases where it doesn't quite, we are still missing a few things. So C++20 is pretty much done. We have committee meeting next week and another one in February in Prague, where we're going to basically do some last-minute bug fixes, and then C++20 is going to be released. So we can't really add more features to C++20 now, but we have a bunch of stuff in the pipeline for C++23, where we're going to have more stuff, and we're going to solve even more of these problems. So this is like ongoing work. So here, I cannot say with 100% certainty what's going to happen, because the committee changes its mind. But okay, so basically, let's look at this again. Like, what kind of problems do we have if you want to do type punning? And we said, okay, the first one, if you want to type pun from type T to type U, this is basically solved. Bitcast basically solves that, okay? What about the second one? If we have bytes and you want to look at them as if they were an object of type T, or float in this case. So it's this case here, right? So this is UB, and this is the more interesting case where we have bytes that come, for example, from a network or from a binary file. We know these bytes represent a value of type widget. So how do we cast it to a widget? That's UB, even in C++20 at the moment, as the draft of C++20 stands. Because here, again, we have not created an object, right? So an object can only be created by these 4 operations. We're not doing any of those. But there is a new paper in the pipeline by Richard Smith, P0593, which relaxes these rules so that we can make this code not UB, okay? So basically what this paper says, and it's a bit of a sad story, because this paper was pretty much ready at the last meeting in July in Cologne. But then at the last minute, it was like the Friday, like the last day where wording could still be voted in, and we just ran out of time. So we just didn't quite finish reviewing the wording of this paper, so it didn't make it for C++20, because that was the feature cutoff date. So it just barely missed the deadline, so we probably have to wait for C++23 to get this paper. What this does is it says, okay, well, let's add something to these rules. So when does an object get created? It gets created by definition by a new expression. You know, if you access and activate a member of a union, and also by an operation that implicitly creates objects. Okay, this like this new magic type of functions. And then basically the trick here is it says, okay, so some functions have this magic ability to create objects implicitly, and these are the allocating functions. If you create an array of bytes, so exactly those kind of situations, right? And it says, well, if one of those functions is called, and then you access an object there, which is not there, and the function is and the program is ub, but then it would not be ub if there would be an object there, then that function implicitly creates that object, and it just basically then just does what you want. Okay, so in this code, this would become okay, because now it says, okay, malloc is one of those functions that can implicitly create an object. So if you do malloc and then you access this object, then it creates it and then you access it, okay, implicitly. And this is the situation. And the other situation where you want to kind of explicitly do this, there is another part of the paper which gives you a explicit notation for this. It's called start lifetime as. And this is now what you do instead of the reinterpret cast, okay? It's a drop-in replacement for the reinterpret cast in this situation where you say, okay, we have some bytes, but instead of just casting it to an object that is not there, we're gonna cast it to this object and also start the lifetime of this object, okay? And this is a bit different from placement new, because placement new is actually calling the constructor. This is not calling the constructor. This is saying, this is like accessing the kind of C++ abstract machine object model and saying, okay, here's some bytes, start the lifetime of an object there. Don't call the constructor, don't actually do anything. Just, I'm telling the compiler that now there is an object there, okay? And it's gonna just take those bytes as a value of this kind of object, and that object is just going to start living at that point. And obviously you can't do this with every type. You can only do this with, because this is not supposed to actually do anything. So you can only do it with types that have at least one trivial constructor, at least one constructor that doesn't actually touch any bits. And if you have an object that has such a constructor that doesn't actually do anything, then you can do this. Then you can say, okay, I don't actually have to touch any bits to create one of those things. So pop, start lifetime as, and then you just create it. And this will enable all these use cases where you have bytes that come from the network, from a binary file, and you just need them to be like an actual object without doing stuff, because you already know that the value is okay. So this is going to solve these things. There is, I think, a slight chance we get the kind of this implicit creation thing into C++20 maybe, probably not. I think we're definitely not going to get this library function in, so this unfortunately will have to wait for C++23, but you know, it's not that far away. It's another 3.5 years. Okay, let's look at the other case. This is also very, very interesting. So we don't have bytes and we want them to be an object, but we have an object and we want to look at the bytes of that object. So it's exactly the other way around. And this should be really easy, right? Like you have an object, you just want to look at the bytes. So let's say we have a function like this, which is supposed to print the byte representation of an object, okay? So you get an object, for example, a float, and you just want to print the bytes. Like maybe you're implementing a hex editor, okay? Let's implement a hex editor. How do you do this in C++? How do you implement this function? Sorry? Copy. Well, yeah, so that's the thing. So people typically implemented something like this, where they say, okay, well, let's just reinterpret cast it to a char star or byte star and print the bytes. So that's interesting. So this line of code actually is okay, because if you remember the rules, byte and char have this special ability that they can alias any other type. So you can actually cast anything to a char star. This is not UB. But what does that mean? So what every compiler actually does with this code is it's going to say, well, then this pointer points to the first byte, okay? But the standard never says that. The standard never says if you reinterpret cast something to a char star, then that's going to point to the first byte. People do this. Like, how do you find like the endianness of your machine? You look at the first byte. But the standard doesn't say that this is supposed to work. It says, well, if you reinterpret cast a pointer like this, you get a pointer of type char star, but it's not pointing to a char because there's no char there. It's actually still pointing to the original object. What does that mean? What value does that have? The standard doesn't really define that. And then you have this thing here where you do essentially, you index into that array of bytes. So you're essentially doing pointer arithmetics on that. And that is definitely UB because there is no array of chars there. So it means you can't index into that array and like increment that pointer because there is no array. There is only a float. Okay. So as I think you said earlier, of course, we now know how to do this. You do memcpy, and this is then going to work. Actually, you can't do bitcast here because bitcast doesn't work with arrays. Yeah, it's a limitation of the language. You can't return an array from a function by value. That's just not a thing that you can do. So you have to do memcpy. You can't use bitcast here. And then it's going to work fine. You can implement your hex editor and everything. But it's sad, right? Because, okay, so I can't touch the bytes. I can't look at the bytes of an object. I have to do memcpy. How do I then implement memcpy? Like, you can't, right? So memcpy then becomes this magic function, which is like the only thing that can actually look at the bytes. And I think this is really wrong because, you know, C++ should be also a low-level language. Like, there shouldn't be room for another language between, you know, the machine and C++, which is more efficient. Like, you should be able to look at the bytes of an object in C++. And kind of in earlier versions of the standard, this was kind of okay, and then in C++ 17, something changed, and now the wording says that this is like UB if you do this stuff. But I think this is a different kind of UB from the other stuff that we saw. There is no real reason why this should be UB. I think this is just a wording defect, basically. This should work, okay? And luckily, there is a proposal in flight, which you're going to look at in Belfast next week at the committee meeting, I think, which is basically proposing to just fix that problem. It says, okay, we need to be able to access the object representation, basically the bytes. It currently doesn't work because of this very unfortunate wording defect. So let's just fix the wording so that the code does what you expect. And yeah, I'm pretty sure we're going to do this for C++ 23. It's a good proposal. I think it fixes a very important thing. So I hope this proposal is going to be successful. So then we're going to fix this problem, okay? There's now one last problem left, a last case where type punning, you can't really do it in C++. And it's this case where you have an object which has something inside, and you want to look at it as if it were several other objects. Because you know the bit pattern is the same, but you can't do it. Except there's exactly one case in the standard where you can do this stuff. There is one special type which allows you to do this. Anyone? No, std complex. So std complex has this really weird wording which says, okay, if you have a complex of t, you can reinterpret caster to an array of 2 t's. And that's fine, just because the standard says it is. And then, okay, so that's useful, right? So imagine you have, like, you need to interface with the C API, so you have a std complex, and then you need to, so this is super useful stuff, and it actually comes up. But then the standard says, okay, we just allow this for this one type. How would you make this work? If you're actually a standard library implementer, how would you actually make sure that this works? We have at least one such person here in the room, so I'm sure could tell us something about that. But so you can actually kind of make this work. So there is this other rule, which we haven't talked about yet. If you have a struct widget and it has an integer inside, and then you interpret cast the pointer to the widget to the integer. Is that okay? Yes, it is okay. There's this one rule which says widget and int are pointer interconvertible because they're both standard layout types, basically like plain old data kind of stuff. Like no virtual functions, no like blah, blah, blah. And then a class and its first member are pointer interconvertible, right? So the pointers are going to, so you can cast between them. And then if you do this with complex, well, you could implement complex like this, where complex has a member, which is an array of 2 t's. And then you can actually reinterpret cast from the complex to the array, right? Because it's the first member, so you can't reinterpret cast between them. They're pointer interconvertible. So then complex works. But what if, I think at least one standard library implements complex not with an array inside, but with 2 members inside? And then that's just not going to work, because you can't convert 2 floats into an array of 2 floats. And even an array is not pointer interconvertible with its first member. So the only way to make this work is, this would always be UB if it's your code. The only way to make this work is to say, well, but I'm the standard library vendor, so the compiler is my friend, so I can just say by fiat, basically, by definition, this is okay, because I've written my compiler in such a way that it's going to do the right thing. And then there's this other special rule about complex, which says, if you have an array of complex, then you can cast them to an array of T, and if you poke that array, you're gonna access the right bits of the, and this is just regardless of how you implement complex. There's no way to make this work where it would not be UB, except the standard says it's not UB for this one type, which is very, very unfortunate. So because this comes up with other types as well. Like one example, I work in audio, this is something that comes up in audio all the time. You have SIMD packs, right? You have a pack of, for example, 4 floats, which you need because you want to do the kind of SIMD accelerated stuff. You want to use these SIMD instructions. But then actually they're just floats in memory. So you need to cast between pointers to floats and pointers to these float packs. And that's something that you actually have to do, except it's UB. And there is nothing you can do currently in the standard to make this not UB, absolutely nothing. Unless you're the compiler and you say, well, this is a compiler type, I know about this, it's fine. But if you're the user, there's nothing you can do to make this work. And I've seen audio programs work fine for 10 years, and then there's a new compiler optimization, then it crashes, and then they say, oh, yeah, it's UB. Okay, so I'm working on another paper, which I think we're also going to look at in Belfast, which basically proposes to have kind of annotation saying, no, but this is fine. So this is probably going to change. This is not the final version, obviously. This is work in progress. But this is the first revision, which we're going to look at next week, which basically says, okay, so to make this work, there should be some kind of annotation that the syntax will probably change, some kind of annotation to say, so this class is laid out in the same way as an array of 4 floats. And then that basically means it's going to be like complex, right? So it's then going to be fine to cast it. And then we can actually remove the special rule from complex and just say, okay, complex also just is laid out as an array of 2 t's, right? And then you also get rid of this nasty special rule in the standard, and then complex can just use this thing. So, but then you can have other types that have this kind of behavior, which is really, really useful. Okay, so let's see where these proposals go. Hopefully they're going through. I think I'm out of time, so that's good, because now I'm at my summary slide. Here are the takeaways. Don't use C-style casts, don't use interpret casts, and please don't use unions, because of these things that we discussed, okay? Instead, in C++17, you can use placement new, you can use memcpy. In 20, you have bitcast, and in 23, you're going to get lots more useful stuff, which is going to plug all these holes and give you all these tools. And this is how you do type punning in modern C++. Okay, thank you.